going to go through to maximise the window after this, but yeah, it will do automatically. Okay, welcome everyone. So I'm going to be very brief, and then before I hand over to my co-host for the evening. So first of all, welcome. Thank you so much for coming out on a Wednesday evening. I think you all got the good news. The reason there are so many people of you here is because you've got the amazing news that it's nice and clear. So the plan for the evening is to hear from our wonderful speakers and then go and stargaze on the lawn. So once you're done in here, just come out to where you came into the building. We will leave you outside for the whole stargazing show. Just one bit of housekeeping. A date for your diary if you want more astronomy is Saturday the 22nd of March. So that's when we're doing our big open day part of the Cambridge Festival. So again, you can when you came in today from 2 until 6 p.m. on that Saturday the 22nd. There's going to be a whole day of astronomical talks and games and activities and things to do and things to see and all that sort of stuff. It's part of the Cambridge Festival. Completely free, no need to book, so just turn up here from 2 p.m. Just to enjoy some astronomy goodness. Cool. Yeah, so this evening today is being done as a special International Women's Day edition of our Wednesday Stargazing evening. So we've got three wonderful speakers and Lisa, who's going to be hosting the whole thing. So I'm going to hand over to Lisa.
Thank you very much, Matt. Hi everyone, welcome to the International Women's Day outreach event. So today you're going to hear from me and then two of our wonderful PhD students who are going to tell you a little bit about all of our research and about some women in science who have either inspired us or perhaps we think that they should get more recognition for their work than perhaps they do at the moment. So I should also highlight, for those of you who have kind of just scurried into the room, we are running a quiz throughout this evening. So please do scan this QR code for the chance to win a book. The Sky is for Everyone. So some of our astronomers here at the IOA have actually contributed towards writing this book, and we have managed to get it signed by them, so you'll receive an exclusive signed copy if you win the quiz. Great. So to kick things off, hi, my name is Lisa Kelsey. I am a Leverhulme and Isaac Newton Trust Fellow here at the IOA, which basically means I'm towards the beginning of my career as an astronomer, but I have completed my PhD. I'm kind of in the next stages of my research. And my research is on type 1a supernovae. So I'm going to be discussing them a little bit to you right now. So what is a type 1a supernova? This is an explosion of a star, but in particular, the star involved has to be a white dwarf star. So these are really compact, dense stars, which are roughly the mass of the sun, compacted inside a region roughly that of the Earth. So very, very dense things. To have a type 1a supernova explosion, there are two mechanisms for this. So either you can have two white dwarfs, which are orbiting around each other until eventually they collide and explode because they exceed this mass limit, or you can have one white dwarf and some other kind of main sequence star, and slowly matter is accreted from that main sequence star onto the white dwarf until again it exceeds that mass limit and explodes. We don't really know for certain what method it is that makes these type 1a supernova, because we have observational evidence or predictions from models for both of these methods. So we think it's likely to be some combination of the two. We identify that these objects are type 1a supernovae by their chemical fingerprint or their spectrum. So you can see here I've highlighted for you in yellow, this is the silicon feature. This is really a key signature of the kind of nuclear physics mechanisms that have gone on inside that star as it explodes. The other feature that you can see there highlighted in blue is oxygen. This really tells us that it can only be a carbon-oxygen white dwarf that has contributed towards this explosion. If it was any other kind of star, you wouldn't have that feature there. Type 1a supernovae have a very characteristic light curve. So this is how their light evolves over time, how their brightness changes. And what you'll see when you actually observe a range of these type 1a supernovae is the brightness increases over time, this nice smooth function, and then decreases and tails off over roughly about 20 days or so. And you can see there is a wide range of potential brightnesses that you can get there. But we can make corrections to their light curves to make them appear a little bit more similar, because as you can see, it's really just an empirical relationship there between the brightness and the time. The ones that evolve brighter take more time to evolve. So if you know that relationship, you can correct down and obtain something that looks a little bit more like this. This is why we call type 1a supernova standard candles, because we know that they should have this peak brightness of about 19 or so magnitudes, so we can use them to measure things like distances in the universe. So this is a standard candle method. It's really quite simple. So I don't know if any of you have ever gone hiking and you've had a torch and your friend's off at the other end of the hill with the same torch that you bought from the same place. You know how bright that torch is, but it looks really dim over there on that distant hill. In the same way we can work out that distance between you and your friend between the hill, you can do the same thing with these type 1a supernova explosions. So we use those to trace the evolution of the universe, how things are changing as a function of distance. But also, you may know of the 2011 Nobel Prize in Physics for the accelerating expansion of the universe. That was all discovered through these type 1a supernova explosions, because their distances were a little bit off what their model predictions from the standard candle method tells us they should be. Type 1a supernovae explode in all kinds of galaxy. So unlike things like core collapse supernovae, they don't require regions of active star formation. So you can have a very old galaxy or a very young galaxy, all with type 1a supernova explosions going off, which kind of complicates things a little bit, because we do see slight differences between these explosions, very minuscule differences. We do see those differences, though, if they're in a high-mass galaxy or a low-mass galaxy, or a galaxy that is actively forming stars, or a galaxy that's kind of dead and towards the end of its life. And so that's what I do. I look at the galaxy environments that these supernovae explode in. So this is some data from my Hubble program, and essentially what I'm doing is trying to understand how these supernovae look different if they're in different galaxies. So I've mentioned to you type 1a supernovae in very far-off galaxies, how we use them to measure distances. But what about type 1a supernovae in our own galaxy? You may recognize this object. This is supernova 1572. So this is a supernova, a type 1a supernova that exploded roughly 500 years ago, and we are seeing nowadays its remnant. This is what remains after that star has exploded. This is this huge ball of gas and dust expanding into this shockwave. This supernova has another name. You may have heard of it as Tycho's supernova, named after Tycho Brahe, who is believed to have discovered this object. Of course, it wasn't just Tycho Brahe. There were observers throughout Europe, throughout the Middle East and China, who all also found this object independently. But I'm going to focus a little bit on Tycho Brahe, but maybe to make you think, was he alone in the discovery of this object? So this is Tycho Brahe. He's an astronomer. You may know of him. He was the one who had his nose cut off in a duel. But these are his observations of this type 1a supernovae. So you can see at the very top, object I. That is the new star that appeared in the constellation of Cassiopeia in November 1572. Reports at the time said that it brightened to a magnitude similar to that of Venus and was visible in the sky for 2 weeks. Even in the daytime, you could see this object. By studying how this star appeared to not really move against the background, they were able to determine how far away it was roughly and say, okay, it's a little bit further away than our planets that we can observe at the time. Now bear in mind, all of this was done before the invention of the telescope. This is all done by eye observations. And this kind of created a paradigm shift in astronomy at the time, because it changed this perception of, okay, these distant stars are no longer fixed objects, they are evolving in time, something is going on here. I think a lot of us have this perception that astronomers of this kind of era were these lone scientists studying up in their distant towers, just doing stuff completely alone by themselves. But this was really not the case. You can see here, so this was an illustration done roughly at the time that Tycho Brahe was observing, where you can see Tycho Brahe and his lovely dog down there, and some assistants helping him with his observations, who were there recording or maybe doing some of those observations themselves. So I want to introduce you to a woman who was actually Tycho Brahe's first ever assistant and his first ever student. This is his youngest sister, Sophia Brahe. So at the time, astronomy was not really seen as a profession that was something that anyone in the nobility would want to do. So both Tycho Brahe and his sister were members of the aristocracy, and it was thought of, okay, why would you want to waste your time doing this? Maybe let's not. So their parents basically said, no, we don't want you being astronomers. Tycho Brahe, being the eldest son, decided, oh, you know what, I'm going to do what I want. I'm going to be an astronomer. It's all going to be great. So he went off, did his own thing. Meanwhile, Sophia Brahe was at home. She was about 10 years younger than her eldest brother, and she was being told, no, you can't do astronomy, maybe you should study like horticulture or botany, that's a more appropriate profession for a young woman in the nobility. And she didn't like that. So she decided that this was in her very early teens. She started learning astronomy all by herself. So she went and looked out for books. She paid translators to translate books that were in Latin into German so that she could understand them, all just out of her pocket money, just because she really loved this topic. And so Tycho Brahe kind of saw this in his sister and said, you know what, my sister's quite talented. I'm going to take her on as a student and she can come and help me. He was a little bit wary because he thought, okay, maybe she might not understand kind of one of the key aspects that we need to do in astronomy of this age, which was actually astrology. So at the time, astrology and astronomy, we might kind of hate it now in that the two are intertwined, but back then, they were really seen as one and the same. And a lot of people who would receive funding for astronomical research were actually gaining funding from people to do astrological predictions. That was what paid for early astronomy. So we often joke in my office that, oh, if it all goes bad, we've got a side hustle as astrologers, but they actually did back in those days. That was how they got their money. So Tycho Brahe brought his sister on, and this was when she was only about 14 years old, and she started helping him with all of his observations. And records at the time, when she was 16, show that she actually took the observations of supernova 1572 that went into Tycho Brahe's work and what he is most well known for. So I think really when we say it's Tycho's supernova, maybe we should be saying it's the Brahe's supernova together, or maybe even it's Sophia's supernova. So Sophia didn't just help with finding this supernova at the time. So this was an observatory that was created in Denmark, which was gained from funding after the 1572 discovery. This is called Uraniaborg Observatory, which was named after the muse of astronomy, Urania, and was established as kind of one of the key research centers of the time. So this kind of castle-looking feature, it actually employed over 100 various students and artisans. There were laboratories there, greenhouses, paper mills, forges, everything you would need to kind of create a huge scientific empire of that time. Sophia took on most of Tycho's responsibilities in actually running the place. So Tycho was often away from the observatory for years at a time, traveling and doing things at different courts, kind of being a court astronomer. So she ran the entire show. She looked after all of these students, all of these experts. If people came looking for their predictions or their astrological horoscopes, she did everything. So she was really kind of a pioneer, and I'd say a research institute leader at the time who should be recognized for what she did. So I just wanted to highlight this quote. This was something that someone wrote in the 1800s, which I thought was particularly fitting. So as I said, type 1a supernovae are actually these double star systems that explode and create this bright feature of light. So I thought it was quite fitting that this quote kind of links Sophia Brahe to this double star system by saying, okay, the Brahes themselves are this double star system that created this explosion in astronomy at the time. So let me read this to you. Denmark must never forget the noble woman who, in spirit much more than flesh and blood, was Tycho Brahe's sister. The shining star in our Danish heaven is indeed a double one. Thank you very much. So we do have time for a couple of questions if anyone has them. I'm going to ask one of you guys to kind of ask the questions. I'm not just asking myself. Thank you.
Okay, yeah, so just put your hands up if you have any questions.
We have time for about 2, I'd say.
Yeah, shall I deliver the microphone?
Just shout and then we'll repeat.
Okay, cool, yeah.
Early on you referred to the critical mass.
Yes.
I have no idea what that is. Can you give a brief explanation?
Yeah, okay, so if I...
I'll just repeat the question for the people online. So it was asking what the critical mass is.
Okay, so this bottom left plot, this is of a white dwarf star, and basically a white dwarf is in this kind of state where the outward electron degeneracy pressure, so that is basically what happens when you have atoms in whatever it is that you're looking at that are too close together, they start to repel against each other, a bit like if you have two magnets of the same dipole pushing apart, they don't want to be any closer. That is what's pushing on the outside to kind of keep this star expanded. And gravity is trying to pull in and collapse that star. And what actually happens is as the mass increases, the electron degeneracy pressure can no longer push out the outward mass of the star. So the whole thing collapses and then implodes and then explodes.
Thank you very much.
No problem.
Any more questions? Yeah, up there.
How many did you record a year of these double white dwarfs and collisions?
So that was how many do we record in a year?
Yeah, so it's really been expanding over the last kind of we've had this big explosion in astronomy. So I've mentioned to you like 1572, they had one supernova just in general. That's why it's called 1572. The way we name supernova now is you have the year and then you have like A, B, C for the course of what they are. We're now getting to the point where supernova in general, we're getting to 4 letters where we're going all the way through A, then all the way through like AB and then AC. So it's really this kind of huge shift. When something like LSST comes online, we'll have even more. So I say roughly per year, those that are classified, we're looking at hundreds to thousands of these objects.
We have time for one more?
We have time for one more quick one.
Why are they called white dwarfs?
Why are they called white
So
dwarfs?
yeah, why are they called white dwarfs?
That's a very good question. I'll be honest with you, I'm not entirely sure I know the answer. So I know there are, so you have white dwarfs, but you also have brown dwarf stars. So brown dwarf stars are very, very small stars that have kind of used up all of their energy and are slowly dim and dead. So white dwarf stars, I assume the name comes from a similar feature in that they're very, very small stars, but they're still shining very, very brightly. So that's what's making them kind of emit this white light. So I think it comes from that. That was a very good question.
Cool, okay. I guess we'll finish the questions there.
Yeah.
Okay, let's see if this works. Thank you. Okay. Oh, hello. Yeah, I think so. If I plug it into the right port, that would be useful. Okay. Let's see if this does anything. Ah! Oh, no. Oh. Okay. I don't know what that is. How do I get rid of this? Yeah. Right, I'm going to unplug this for a second while I close this. Wait. I'm confused. Is that... Sorry.
How many PhDs does it take to fix the computer?
A lot. No, oh, we're making it worse. It's my fault for having error messages that I don't get rid of. Okay, and then if we just...
And then if you sort that one.
How? You know what? If I do that and then... Oh, not again. No.
Tab over.
Just get to stare at my face for a bit longer.
There you go.
Beautiful. Okay, we got there eventually. I'm sorry that my technical skills are somewhat lacking. Right. Hello. I can't work a computer, but I am a PhD student. Hello, my name is Frances Rigby. I'm a 4th year PhD student here at the IOA, so nearly done with my PhD, which is mildly terrifying. And yeah, so this is my face that you've already seen. So yeah, 4th year PhD student, and I work on exoplanet interiors, atmospheres, and habitability, which is quite broad. But firstly, I don't know if we all know what an exoplanet is, so I'm going to tell you anyway. It is a planet that orbits a star that is not our sun, so it's outside of our solar system. And we're going to start by looking at this rather complicated looking diagram, but we'll go through it slowly. So along the bottom, so the x-axis, this is the orbital period, so how long a year takes for these planets. And then on the y-axis, this is the size relative to Earth, so what is its radius? And you can see that down at the bottom, we've got these rocky planets, which are like the Earth, they're very small, they're made of rock. If you push a rocky planet closer to its star, so further that way, it's going to get much hotter, and it could have lava on its surface. Then as we get even bigger, we're going to incorporate things like water, things like hydrogen in its atmosphere. And then right at the very top, we've got things like gas giants. So like Jupiter. And then if you push Jupiter closer to its star, it would be much hotter. It could be a hot Jupiter, which is a very imaginative name. So then, can we see my cursor? Yes, we can. Beautiful. So this down here, this little key, is showing you the different detection methods. So the different ways that we've actually found these exoplanets. And I'm not going to go into a huge amount of detail about these, but we will talk about one of them, which is the transit method later on. So the area of this diagram that I care about is this section that I've highlighted in pink, which looks pretty arbitrary, but this is between 1 to 4 Earth radii. And these are a regime of planets called sub-Neptunes. So they're anywhere between the size of Earth and Neptune. And the reason that these are really, really exciting planets is because they can encompass such a wide variety of different compositions. So you can have things like super-Earths, which are literally just like the Earth, but bigger. So they've got quite heavy atmospheres, they're really rocky. And then you can have things like mini-Neptunes, which are just smaller versions of Neptune, with lots of ices, lots of water, lots of gas. And then you can have pretty much anything in the middle. So this regime then opens up things like Haitian worlds, which are planets with oceans at their surface underneath a hydrogen atmosphere. So yeah, so this regime contains a lot of different kinds of planets. And this is just a diagram of some of these possibilities. So we've got one on this side, which is a rocky world, where we've got this rocky layer and then a hydrogen atmosphere. All the way at the other end, we've got this mini Neptune with these icy layers in the middle. And then we've got this Haitian world in the middle. The word Haitian isn't some kind of fancy Greek word. It literally just is hydrogen and ocean mashed together. So, yeah. When I first read it, I read it as Haitian, and then was very bluntly told by my supervisor that that was wrong. So yes, Haitian worlds. So these are some of the different possibilities. And how do we actually find out which of these is real for a given planet? Because all we really know for most of these planets is its mass and its radius. Okay. So what we do is we take the mass and radius, we plug it into something called an internal structure model, which is what I spend most of my time doing. And then what you get out are lots and lots of different possibilities of what this planet can be. So how do we actually narrow that down? Well, we start to use atmospheric data. If we start to plug this into the model, we can rule out some of these possibilities of what the planet could be. So how do we get this atmospheric data? This relies on something called an exoplanet transit. I really like this animation. I think it's really useful. So a transit, oh no, not again. Let's try this. Oh, that's not going to work, is it? Okay. Give me a minute. Any ideas of how to get rid of this? Because I have no idea. That way. Sorry.
I'm worried it's going to do an update.
Can we just, like, if we switch off presenter view somehow, is that going to work?
I don't know. Let's just cancel it. Hopefully it won't pop.
Okay, fingers crossed. Okay, please. Okay, so exoplanet transits. So this is when the planet is passing in front of the star relative to our line of sight. So you can see that you get this dip in the brightness that we receive from the star because the planet is blocking out some of the light. And if we look at the ratio between when the star is in, like when the planet is transiting and when it's not transiting, we can start to figure out what the planet radius is, which is really, really important. And even better than that, we can use something called a spectrograph. So when the planet is in front of the starlight is also shining through the planet's atmosphere. So the atmosphere is going to be made up of some kind of chemicals, if it's there. The light then interacts with the different chemical species in the atmosphere. And the different wavelengths or colours of light react with different chemicals differently. So what we get when we look at its spectrum are different sort of slices out of the spectrum based on the different chemicals in the planet's atmosphere. So we can figure out what it's made of. And okay, I'm going to warn you, the next slide looks very complicated, but we'll go through it slowly. So this is some real data of what an exoplanet spectrum might look like. So On the x-axis, so going across this way, this is the wavelength or colour of light. But this is in the infrared, so it's not the kind of light that we see with our eyes, it's infrared, it's a longer wavelength than that. And then going up the y-axis, this is the depth of the transit, so just the amount of brightness that we're receiving. And then the different chemicals are going to cause these different bumps in the spectrum that we actually see. So this is after people in our research group have reduced the data and done some analysis on it, and you can see this is the best fit result that we end up getting with these different bumps based on what chemicals are there. So we've got CH4, which is methane, and we've got CO2, which is carbon dioxide, which are both very recognisable chemicals to our lovers. And then what we can do is by saying that we see some of these molecules and then not other molecules that we might expect, which is something like ammonia for this kind of planet, we can start to rule out different possibilities about what this planet's going to be, because some of these chemicals might dissolve in an ocean if it's possibly there. So that's how we use this atmospheric data to try and figure out what's inside these planets. Okay, this data, as you can see from up here, comes from JWST, which stands for the James Webb Space Telescope. You might recognise this quite famous picture of it from NASA. So this launched back in, I think it was 2021, around Christmas. It might have been Christmas Eve or something like that. So this is the James Webb Space Telescope, and that's really, really important for our exoplanet research because it's giving us such high quality data of these exoplanets. So it's got lots of different instruments on board, including spectrographs, which allow us to look at these planetary atmospheres. So this leads me nicely onto a female astronomer that inspires me. This is Dr. Jane Rigby. To the best of my knowledge, no, we are not related. Who knows? Should do a 23andMe and see if we actually are. But anyway, this is Dr. Jane Rigby. She is a senior project scientist for the James Webb Space Telescope. And this basically means she is in charge of making sure we get the best science out of JWST that we possibly can. So Dr. Rigby did her PhD at the University of Arizona, and she now works for NASA. So like I said, she's the senior project scientist for JWST, which is a really important job. And you can see her there in front of the telescope before it launched. You can see the hexagonal mirrors that are so iconic for the Space Telescope. And she's also an astrophysicist at the NASA Goddard Space Flight Center. So she works on things very, very different to me. She looks at galaxies, particularly star-forming galaxies, and she has over 100 peer-reviewed publications, so she's excellent at what she does. The other thing that really inspires me about Dr. Rigby is her work to do with inclusivity in astronomy. So this here is the logo for the American Astronomical Society's committee for, let's see if I get the exact wording right, because it's quite a long sentence, for sexual orientation and gender minorities in astronomy, or SGMA. So this committee is really, really important because it's working to promote equality in astronomy for minorities, including LGBTQ+ people. And they have goals to do with ending hiring and workplace discrimination for gender minorities and creating a professional environment that's really respectful and, promoting things like networking, mentorship, and that sort of thing, which is really, really important. And last year, before the change in presidency, she was awarded the Presidential Medal of Freedom by Joe Biden for all her work in both JWST and her work to do with inclusivity in astronomy. So I'm going to end with this quote from Dr. Rigby that I really, really like, which is, "Do fabulous science, be fabulous, and be kind." So yeah, thank you.
Okay, so I'll be in charge of questions this time. So does anyone have any questions? We have time again for 2 or 3. Yeah.
You seem very passionate about exoplanets.
Yeah.
What, from your perspective, is the most exciting aspect of them?
Most exciting aspect of exoplanets. I think it's that we get to see planets that are just so vastly different to the ones that we're kind of used to in our own solar system. So these sub-Neptunes, we don't have anything like that in our solar system. So we get these windows into completely different worlds, basically. Or these hot Jupiters, which no one thought could exist because it's Jupiter right next to its star, which completely blew people's minds back in the 90s when they were first discovered. So, yeah.
Excuse me. That was fantastic, by the way. I really enjoyed that.
Thank you.
I love the graph towards the beginning that showed the relationship between sizes and going around its sort of its star. I wonder, I'm really into moons, particularly Jupiter's moons. Would it be the same table because the planets are in fact following the moons are following the same principles because they're going around the star, or would you make a new new table based on its parent planet?
Yeah, so I'm going to scroll back to this slide and make sure we're talking about the same thing. You're talking about this one? Yeah. So if it's talking about its orbital period, moons are tricky because obviously they've got an orbital period going around their planet and then around the star. So I guess you could probably plot both of them. But we haven't detected I think we have detected exomoons, but not many of them. They're very hard to find if we have detected any. So it would be lovely if we had a plot that was this full of exomoons, but yeah, I don't know if that answers your question.
Okay. Is there one more, or should we finish up?
I think I probably ran over with all my technical difficulties. So.
Perfect. I'll finish up then.
Okay, amazing. Thank you, everyone. I'll take my laptop now.
Okay. Okay, that looks promising. Okay, perfect. So, hi everyone, thanks so much for having me. It's really great to be chatting to you all today. I'm Leah, I'm a third year PhD student here at the Institute of Astronomy. Today I'll be doing a quick deep dive into my own work on supermassive black hole feedback, and then I'll be telling you about my wonderful supervisor, Alex Amon, who's not only been a fantastic mentor to me, but she's also been leading the field in this area for years now. Perfect. Okay, so to get started, I think it's important we understand the different types of black holes that are out there in the universe and how kind of surprisingly common they are. I think we tend to think of black holes as these kind of rare objects lurking out there in kind of the depth of space, but actually they exist across a very wide range of kind of scales and in different environments, and they're actually found all over the universe. So we generally split black holes into three main types. So the first on the left here are stellar mass black holes. These occur when massive stars a bit heavier than our sun reach the end of their lives. Once they've burnt through all their fuel, their core collapses under its own gravity. And if the star is heavy enough, this collapse kind of goes on and kind of escalates, and we end up getting a black hole forming. Now, these black holes are typically between around 5 and 10 times the mass of the sun. And we think there could be millions of these kind of little black holes scattered throughout our galaxy where previous stars have died. Okay, then we get on to intermediate mass black holes. So these are kind of somewhere in the middle, the kind of missing link between the smaller black holes and then the really giant ones. These are maybe hundreds or thousands of times the mass of the sun, and we think they might form when smaller mass black holes kind of merge together or in very dense centers of star clusters. But we're not entirely certain, and they're also really hard to detect as well, though we're kind of just about starting to find some promising candidates. Okay, then finally we have supermassive black holes here. So these are about millions or even billions of times the mass of the sun. We think they sit at the center of nearly every large galaxy in the universe, including our own. Our own galaxy has its own black hole at the center. How they form is still a very open question. We think they could form from these smaller seed black holes at the start of the universe that have just had a long time to grow and merge with other black holes, but we're not entirely sure still. Okay, so supermassive black holes are what I'm personally most interested in. And as I said, we now have very strong evidence that they exist at the center of most galaxies in the universe. Now, one of the most direct lines of evidence of this comes from observing the motions of stars. So in our own galaxy, the Milky Way, we've tracked the motions of stars near the galaxy center for decades now. And we've seen that they appear to be kind of orbiting some very massive object at the center, but something that's completely invisible. If we look in a bit more detail at kind of the speeds and the shapes of these orbits, we see that they must be orbiting something incredibly heavy that must be around 4 million times the mass of the sun, and it must be located in a very kind of compact, small area. The only thing that really fits the picture here is a supermassive black hole, and over time we've kind of done a lot more investigations and kind of taken more observations, and we've really kind of built up a clear picture that supermassive black holes are a really fundamental part of galaxy centers across the universe. Now, of course, we usually associate black holes as something that pulls matter in. But I think what's really interesting and what I work on is the fact they can also push matter out and to incredibly large scales. So this process of pushing matter away from supermassive black holes is called black hole feedback, and it plays a really crucial role in kind of shaping galaxies. Now, there are two main ways that black hole feedback works. So firstly, we have the quasar mode. This happens when the black hole is actively feeding, kind of actively pulling in huge amounts of gas. And because this gas is falling so fast, it gets very, very hot. And eventually this then powers incredibly fast winds that actually push the gas outwards, and we get these very large outflows from the center of the galaxy at very high speeds. The second type is called the radio mode. This happens when the black hole isn't kind of feeding as quickly, but it still ends up launching these jets that come out, and they're very kind of fast-moving particles that shoot out into space at very high speeds. These jets can travel far outside the galaxy itself and kind of go beyond to very large distances away from the black hole near where they began. So we've learned over time that black holes don't just kind of sit quietly at the center of galaxies, and that in addition to pulling matter in, they also have a role in kind of pushing matter outwards as well. Okay, so to help us understand what's actually going on with this black hole feedback, scientists have kind of built these computer simulations of mini universes on our computer to kind of test different models of black hole feedback and see if it looks like what we see out there in the actual universe. So with these simulations, we input kind of all of the laws of physics we know. So we input kind of how we think stars form, galaxies form, black holes form, etc. So on the screen here, I show an example called the Fable simulation, which is a simulation that I ran as part of my PhD. What I'm showing here is something called the cosmic web, which is just essentially the most zoomed out picture of the universe that we can essentially think of. It shows this network of kind of galaxies, which are kind of the dense parts here and the very bright spots where we have a lot of hot gas. And then these filaments or strings between galaxies, which just shows where the gas is flowing and kind of feeding and going in and out of galaxies. Now, one really important discovery from these simulations is that you can't make realistic galaxies unless you have this black hole feedback. Essentially, if we leave black holes out, galaxies just grow and grow, kind of unregulated. They form way too many stars, and they don't look anything like the galaxies we actually see out there in the universe. When we then add this feedback, we get these kind of jets, and we have these winds coming out from black holes, and then things start to look a lot more familiar, and like the galaxies we actually see through our telescopes. Now, there are many teams around the world who have run these simulations. It wasn't just us here in Cambridge. And they've made predictions for how strong they think feedback should be. Now, the issue is none of these simulations agree with each other. They have no idea on how strong we actually think black hole feedback is. Some of the simulations say feedback has to be super extreme. We have these powerful jets kind of blasting gas out of galaxies. Whereas others say that it's much weaker and it's more of kind of a gentler heating of kind of the center of the galaxy. So the plot I'm showing here just helps us see this. It shows the predictions for how extreme feedback is made by these different teams around the world who have run their own simulations. So this is what's shown as the different colored lines here. So on the y-axis, the further the line dips down from 0, the stronger the feedback is. That essentially means that more gas has been kind of pushed away and the matter has ended up more spread out. So this red dotted line here, for example, shows a simulation which says that feedback is very extreme. We have these very strong jets, whereas this kind of orange line at the top here is a more weak scenario. Now the issue is we don't know which of these simulations is right. And as you can imagine, each of the teams who run these simulations are very passionate that their one is the right one, and this ends up with lots of disagreements when you get to conferences and lots of arguments. So this brings me to my supervisor, Alex Amon. So Alex spent some time here in Cambridge, but she's now an assistant professor at Princeton University, where she leads Dark Lab. Dark Lab is a group of graduate students and postdocs who all kind of work together to answer these really fundamental questions about our universe. So she had a really great idea. She said that instead of scientists kind of endlessly arguing over which simulation is the right one and kind of arguing their own case, she said, why don't we just try and observe black hole feedback directly? She said if we could actually see how far kind of black holes are pushing the gas out, then we could actually know for sure how powerful black hole feedback is. She suggested we work together and we use some exciting new observations that came from the Atacama Cosmology Telescope, which sits high up in the Chilean desert. These observations map out where the gas is in the universe, and then we can know if it's been kind of moved or pushed around, and therefore how strong the feedback is. And when we did this, we found something that we didn't expect. We found that none of the simulations were right, and that actually feedback was much more extreme than most of them. And as you can imagine, this upset a lot of the simulators, and we ended up having a lot of more arguments at conferences. We found that at least the observations showed us that these jets from black holes can travel much further distances than we thought they could, and they're clearing out gas from very enormous regions of space. So this was some of the first real evidence that black hole feedback was maybe so extreme, and maybe our simulations that we'd argued about for so long were maybe potentially wrong. So why does this all matter? Why do we need to know how strong this black hole feedback is? It's tied to a big question in cosmology that's called the S8 tension. So in cosmology, we're trying to answer these very fundamental questions about the universe, kind of how it started, how much matter it contains, how it will end up. And if we want to learn about this, a good place to start is knowing how structure formed in the universe, so understanding how it evolved. What we do practically when we're trying to understand this question is measure something called the S8 parameter, which just tells us if the matter in the universe is very clumpy today or if it's very kind of diffuse and spread out. Essentially, it's a key parameter we need to know for sure so that we can then go on to predict the future of our universe. Now, there are two main ways to measure this clumpiness. One uses the galaxies we see that are quite close to us today, which are most of these data points that lie on the left here. And one uses the first light from the universe, which is called the cosmic microwave background. You might have heard of it. Now, the issue is, when we make these two measurements of how clumpy the universe is with these two methods, the answers don't agree. You can see here that the measurements where we use local galaxies are kind of offset to the left and give us a lower answer than when we use the cosmic microwave background. And this is an issue because these methods definitely should agree. If you have two different ways of measuring the same thing, they should give us the same answer. The fact they don't agree suggests that we might be missing something kind of very important into how our universe works, and then it might be time to rethink some of our really basic ideas on how we think the universe is evolving and how it might end up. So how does this connect to feedback? So Alex proposed that we should kind of hold off on thinking that our model of the universe is all wrong because of this S8 tension, and we should remember these measurements that we made of strong black hole feedback. She said that when the feedback is more intense than we previously thought it would, again, push matter out to very large distances, and that would mean things in the local universe look a bit less clumpy. So it would give us a lower value of S8. So this will explain why these measurements using galaxies are giving us this lower value of this S8 parameter, this clumpiness. And Alex and I kind of accounted for this extreme feedback for some of the first time in these kind of local galaxies. And we found that when we do the S8 values now agree quite nicely. Now, there's still a lot of work to do to kind of convince the broader scientific community on whether the S8 tension is resolved. And I think that Alex has had to kind of fight her case a lot to say that extreme feedback is real and that it kind of solves this problem that we're having in the universe. But I think it's really encouraging and exciting to see that our model of the universe might not be completely off track. And we've managed to get the same answer for S8, so maybe things are better than we thought. It's been really exciting to work with Alex kind of throughout my PhD and watch her kind of come up with ideas and test them. She's really been kind of such a fantastic role model and see her kind of be a great representation of kind of a woman in science and seeing the things she's achieved. And I'm really excited to kind of see what she comes up with next and see what questions that she's kind of yet to answer. Thank you.
For a couple of questions. Does anyone have any questions? Yes, one over there.
Your first slide showed the picture of the black hole.
Go back.
I understand the blackness.
This one or this
The
one?
next one. No.
Uh-huh.
What's the orange and red?
Yeah, so this was kind of one of the first images we ever had of a black hole directly. Essentially what we're seeing in the black here is the black hole's shadow. And what's happening is the gas that's kind of circling the black hole and kind of getting very, very hot, its light has then been bent because of the very strong gravity that occurs near a black hole. It's kind of the strongest gravity we could ever imagine. And that light has kind of got bent round, and then it comes back towards us. So essentially, we see this ring around the black hole, but then we see the shadow of it itself in the center. So essentially, everything just getting very hot around it.
And we've got time for one more question.
Is there a possibility that there are black holes that are larger than supermassive black holes, or are they like all around the same size, or could there be some that are like 20,000 times bigger or so?
So we know that there definitely should be a limit, but above supermassive black holes, there's also gargantuan black holes. And these are absolutely enormous. These are 1 with 10 zeros times the mass of the sun. We are not too confident in kind of how these would form, but they've been shown in simulations that they exist.
I think we can squeeze one more last question in. Go for it.
How many types of black holes are there?
So we think from this here that there are 3 different main types of black holes. But in terms of the actual number of black holes in the universe, millions and billions.
Great. Thank you very much. Okay, now before you all go off observing, I know you're all very keen to leave, it is time to announce who is the winner of The Sky is for Everyone. There were some people who were very, very, very close, but there was one person who had a perfect score of 150 out of 150. It's absolutely amazing. So if Jamie Cakebread could come and find me as everyone is leaving, you can come and collect your book.